Hi everyone, welcome to Deep Learning Talks. So in the previous videos, we have talked about token embeddings. We have talked about token IDs, tokenization. We have also talked about single head of attention, multiple heads of attention. Now, in case of a transformer, in especially both of these blocks, what are the trainable weights? What do we mean by trainable weights? So trainable weights or learnable weights are used interchangeably, or they are also known as the parameters, right? So they are not the hyperparameters, obviously. Hyperparameters are controlled by you as an engineer, as a scientist, but these are the trainable weights that the model learns throughout its training. So what are them? What are these trainable weights? So the first trainable weights that we talked about was token embeddings. We talked about token embeddings, and we noted that token embeddings might not be the best when we start with them. They are obviously higher dimensions, right? They are higher dimension representation of each token. For example, a 512 dimension representation of Puru as a token. In the start, there might not be any correlation or any alignment between the vector representation of Eiffel and the vector representation of tower, right? So, but we want that these embeddings should capture the meaning of Eiffel and tower, and they should also capture the contextual representation between both of them. All of these token embeddings are learned, let's say a million, and each of these token is represented as 512 dimension vector. Then 512 million elements are learnable weights. So we can simply say at an abstract level that token embeddings are learnable, right? Token embeddings are trainable. In some cases, positional embeddings are also trainable. We talked about this. Attention is all you need. The paper captures to positional embeddings as static, right? But the GPT family treats the positional embeddings as trainable weights, trainable matrices, right? So they are also of the same size, which is, let's say, dk. Assume that token embeddings are dk. Positional embeddings are also going to be dk, right? The same dimension. Now, when we go down in the attention block, we also see key, query, and value. So key had a weight matrix known as WK, query had a weight matrix known as WQ, value had a weight matrix known as WV. All of these three matrices are also trainable or are also learnable. Now, when we go down and if we have multiple heads, we concatenate all the heads and multiply it with the projection matrix. The projection matrix known as WO is also trainable matrix. So what we have realized, all these matrices are trainable that we talked about that were kind of unknowns and ambiguous to us. All of these weight matrices are trainable. So we don't need to have a static algorithm, a static function that will give us the best embeddings, that will give us the best key, the best query, and the best value. We will all, so the narrative goes like this, that we'll learn all of these on the way while training. Now when we'll realize that when we will do residual and add norm, this is also an operation that happens or a sublayer that happens after the multi-headed attention. So we will realize that the normalization would have scaling and shifting vectors. They are also trainable. Now when the normalized output goes into feed-forward neural network in any transformer, we would realize that the weights and biases in the feed-forward neural network are obviously trainable. So all of these matrices that we talked about are the trainable matrices. Let's revisit them quickly. The first thing is token embeddings. The second thing is positional embeddings. They might or might not be trainable. Then WK, WQ, WV, right? All the key, query, and value matrices. Then WO, the projection matrix. Then scaling and shifting vectors as part of normalization. Then the feed forward neural network has weights and biases. So let's say the feed forward neural network have multiple layers. At each layer, at each neuron, it will have a bias, and at all the edges, it will have weight vectors. So all the weight vectors sitting on the edges and all the biases sitting on the neurons are going to be trainable also. Thank you. I hope this was helpful in understanding what are trainable matrices or what are trainable parameters in case of a transformer. So it's a very important interview question, and a lot of people assume or fail to realize that these parameters are trainable. Some people have an assumption that token embeddings might be generated by another algorithm, which is a static word to vec kind of an embedding algorithm. Some people have an assumption that positional embeddings can be discrete or they are always non-trainable. And some people also assume that scaling and shifting, the normalization follows a simple z-score or z-scalar formula, and it is all the time it's non-trainable. So yeah, I hope it disambiguates the whole idea of what are the trainable weights parameters in case of a transformer. Thank you.